Okay, so welcome. Hopefully this week goes better than last week. Welcome to System Administration. Today is November 20th. We'll finish up that chapter 7 on processes. And according to the syllabus, I went back and looked at the syllabus. It looks like we need to finish up, excuse me, chapter 8 and 9 today. We might not be able to get through all of that. So we'll try to get through what we can today in the time that's allotted, and yeah, definitely gonna get the virtual machine going today too, hopefully. Okay, all right. So what we'll do is we'll just get right into it because again, we have a lot to cover and unfortunately not a ton of time to work with it. All right, so let me pull up chapter 7. Okay. All right. So last week, what we were able to get into, if I remember correctly, and somebody please correct me if I'm wrong, was we talked about processes and what is a process and how the forking works and how a parent process will wait until a child is completed with its execution, what a zombie state process is, some of the other states, we talked about that, and then how to list out processes using the PS command, the current processes who are running or waiting and doing other things. Let's see. So we finished off that section, if I'm not mistaken, right? And because of some issues with the virtual machine, and there was something else. I don't remember what. There was something else that was an issue. I don't remember what it was, but we ended here where we talked about jobs. All right, and this is what we were about to get into. And so a job, we could talk about that, like any processes that are part of a job are members of the same process group. So a job is multiple commands, multiple processes that will be running kind of together. Okay. Now, there are some things that are foreground processes and some that are background. So anything that's running in the background, we don't see it. Foreground processes are ones that we will see in the foreground. So background processes can't do anything about like reading input or receiving inputs from the user, right? But they might be able to write to the terminal, meaning we might be able to see some output from them. We just can't do anything to them. We can't interact with them in the form of giving input to them, okay? A job could be stopped. And we'll talk about how to do some of this. I think that's in the killing processes section. We'll talk about that as well, okay? Okay. Some processes are started by the system and not from you, not from a shell prompt. So they, a lot of times you'll see them as the root processes. So you can't bring those to the foreground, but because they are not started by the shell, and so they cannot be brought to the foreground in a shell. All right. So how do we take a job and say, okay, I want to run this in the background? And you can use this ampersand at the end of a command, and what will happen is when this ampersand is seen, it will tell you what the job number is. All right, the job number 1 and the process ID of this new child process, right? And then it'll immediately just come back to the shell prompt. So if you didn't have this ampersand, the sleep command is just a wait. It doesn't do anything. It just waits. Okay, so if we didn't have the ampersand here, what would happen is sleep 10,000. If I'm not mistaken, that's 10,000 seconds, but I'm not positive. 10,000 seconds or milliseconds. I'll have to look that one up. I don't remember off the top of my head. So when you would run that is it would just wait. It would just wait and do nothing. And then finally, once that time has passed, it would jump over to back to the terminal. All right. But this ampersand makes it run in the background. So it doesn't wait for this process to end before it gives us a new prompt to deal with. Okay. All right. So again, the shell does not wait for the child process and redisplays the shell prompt immediately. Okay. All right. Now, when an ampersand is used as part of a pipeline, so notice there's multiple commands in this pipeline. You remember how pipelines work. So the output of this command gets put as the input to this command. The output of this gets put as the input to this, right? And then this mail command, would give you a mail, would give you an email, right? So this ampersand puts the whole thing, the whole job to the background, right? But the only information we get, the only process ID we get information about is this last one, the mail command. Okay. Each one of these other processes has their own unique process ID, right? But the only process ID we get is this last one. Instead of showing us the job with all these other process IDs, it just shows us the job with the single process ID, the last one. Okay. All right, so if we want to see what jobs, right, are going on, we can use the jobs command, and it would show us this sleep command is running. It's running in the background right now. Okay, if we want to bring that job to the foreground, meaning make it run in the shell, we can do that with the FG command, the foreground command. And what will happen is it'll be brought, and again, the sleep command, what does it do? It just waits. So what we're doing is now we said, okay, we just want to wait. I want to wait until this time has elapsed. Now, let's say that you bring something to the foreground, or let's say something's running in the foreground and you don't want it to. You need to get back to that prompt because whatever this is taking too long and you want to push it back to the background. You can do that first. You have to get a command prompt in order to do that. So you suspend, Control Z to suspend the current process. Right. So Control Z will give us back to the command prompt, and it will take that process that is running in the foreground, and it will suspend it. Okay, it is immediately placed in the background and is suspended. So if we do that, remember PS command was a process listing, right? PSJ will tell us stuff related to jobs. So it gives us some status. We'll talk about what these status codes are in just a moment. Okay. But if we do the PSJ, then we get this. I don't remember what. I can't remember the PPID. I can't remember. But process ID here, process group ID, so it's part of in this same command window. Okay. So the example sleep command is currently suspended. That state would be T. Again, there's a chart here. It's on the next page. No, it's in the killing processes section that tells us what these statuses are. Okay. If we want to start the suspended process, use the BG command with that job ID. So BG%1, so the job ID. We'll then take that suspended process and we'll start it up. Because right now it's background and suspended, which means it's not running. But what we want is we want to run it in the background. So that BG%1 will take that process that's suspended in the background and start it running in the background. Okay. So again, going back, Control Z suspends the process, puts it to the background, suspends it. So it's not running, it's not doing anything. All right. This BG with the job ID will take that background suspended process and start it running again. And so that's how we get the process to be in the background and running. So it'll tell us, tell us what that process is, and it'll get, and it's now we have a command prompt again, and it's running, and it's in the background. So we don't see it, and it's running. Okay. All right. This is where last week we kind of had a breakdown on this, was because I wanted to be able to do some of these guided exercises, but unfortunately, virtual machine, I couldn't share it appropriately, and so we had some issues with that. Right. So we will do some guided exercises here today. And during the first break, if I remember, I may need to make myself a note. I will upload. I don't think I have uploaded the chapter 8 and 9 stuff yet, so I will go ahead and get that out to that class materials folder during the first break here. Okay. All right. So let's talk a little bit about how to send signals to a process. So that Control Z, in a sense, send a signal to the process to tell it, hey, I want to suspend you and I want you to be in the background. Okay. So there's different other ways that we can send signals to process to get them to do things that we need them to do. So the title of this section is Killing Processes. So really what this is primarily going to be used for, that we're going to talk about, is how to take a process that's running and kill it and get it to stop executing. Sometimes, for some reason or another, there's a process that is running and it's causing problems, or whatever it was that it was doing, we no longer need it to do, and it's taking up system resources. And so what we want to do is we want to stop it, okay, and we want to get rid of it. All right, so here are some different signals that we can send. Okay, and we'll talk about the commands to do that. But here's some different signals, signal numbers, and what the name is of that. Okay, now this 15 signal number, terminate, it's the default, meaning if we don't give it a signal number, if we don't particularly give it a signal number, this is what it will try to give it. Now, this is a terminate command that is intended to take the program, take the process, and stop it, and get it, and basically kill it, and get rid of it. Okay. Now, this particular one can be blocked, ignored, or handled. Okay. So this is a way that if the process is in the middle of doing something that it really shouldn't stop right then, it's, hold on, let me finish this up, and then I will terminate. Okay, this is what this signal does, is it tells the process, we need you to terminate, finish up anything that's necessary, and then we'll go ahead and get rid of you. Okay, so what if the process what if the process doesn't want to behave, doesn't want to do that? So an example of this, maybe an example of not this particular signal, but something you may have run across, is if you've ever tried to shut down your computer and you get a message that says, hey, this program is, we're waiting on it to close before we shut down the computer. I've gotten that a few times here on this machine. Usually for some reason folders, if I have folders open in a window, but it'll say, hold on, we're waiting, we're getting rid of this, we're closing this out, and then we'll shut down the computer. But I do get an option. I do get an option that I'm saying, I can say, no, I want this to shut down now. I don't want you to wait any longer for this other thing to shut down. I need the computer to shut down immediately. So this would be kind of the kill command. So if the process needs to be immediately terminated, no matter what, like I can't wait for it to finish up what it's doing, it has to be terminated, we can send this other special command, this other special signal, the kill command, that will immediately get rid of it. Okay. Some other ones that aren't necessarily getting the termination going is that if a process is stopped, we might want to say, okay, we don't want to kill it, we just want it to stop doing things for a little while. until we tell it not to, until we tell it to continue, right? So we can tell a process, hey, you're stopped, go ahead and start up again, okay? And it can resume the process. We can send it the stop command, which would suspend it, okay? This is, again, the control Z. We talked about that in the last section. The control Z command, the SIG stop, the keyboard stop command. What that will do is that will suspend a process, but it cannot be blocked. Sorry, no, it can be blocked. This one, the keyboard stop can be blocked if it's in the middle of doing something. The stop command cannot be blocked. Okay, the process must obey immediately. Okay. So see, these are some of the signals that we can send to a process to get them to do what we want them to do. So here, the kill command, all right, now be careful with this. It's the kill command, but it doesn't just kill processes. It can stop them, it can kill them, it can do other things. Okay, so this is kind of a list of these, like, so the previous page had a list of the most important ones for you to know. This if you kill -L, it tells you about these things. Okay. Is there a question? Okay, yeah, you will need root access, I believe. Well, no, because clearly the student is able to do that. I think you're only allowed to kill processes that you started, or that you're the owner of. But if you want to kill like a root process, you probably, I would imagine you do need root access. Good question, right? Because we don't want to go around killing everybody else's processes, right? So the kill command will send a signal by that ID. So this list of IDs that we talked about before, you know, like the term, like this term, which is the default, right? Okay. We can send any signal, any of these 20, but again, SIG term is the default because it is what you're most likely going to be doing. You're most likely going to be trying to politely terminate the command. Okay. We can also have a kill all command to be able to get all processes that are in a certain criteria. Okay. Again, if you do kill PID on its own or kill all command pattern, it gives the default signal, gives the default signal to terminate. If we say kill dash whatever PID, it takes that process ID and it sends a particular signal to it. Okay. All right. So pkill is a little bit more advanced. They can use advanced selection criteria. Okay. Let's look at, I think the next page has some good examples. Has some examples of how to use this. So one of the things that we can do is I guess there, thought there were examples on this next page. This must be an older version of this. Okay. So one of the things also that we may want to do is take a user who's logged into the system and everything they're working on, everything they're doing, and log them out. Like if I mean, in the extreme situation, you might have a circumstance where somebody's hacking the system or something, and you want to get them out, immediately. In some other situations, you might have a user that accidentally left themselves logged in, and they need to be logged out because they've left for the day, and we don't want their stuff hanging around there. So there's all kinds of reasons that we might want to do this. Okay. But what we can do is we can look at who is logged in, right? Using the -F option on the W command, right? So the W command to use users currently logged in, right? And where they're from. So the -F tells us where they're from. So here you might see, okay, student is logged in. These are the local, right? And then this is where student might be logged in from a different place. Okay, so if they're logged in remotely. And one of the things that we're supposed to cover today, if we can get there, is the SSH for how to log in remotely. But for now, we just want to acknowledge that you can log in to a local machine from a remote desktop, from a remote computer connected to the network. And this is so this would tell us where they're connecting from. And this tells us what they are running. So notice here, we are logged in as student. Sorry. We are logged in as student on server X. We are running this. I didn't highlight that. Right, we are running these two locally. Notice the W-F, that's what we're running right now. Right? And there's something else that we're running as well over here. All right. Root has its own thing. Some guy named Bob is also, but there's another student account, user student, that's logged into this computer, into this system from a remote desktop. Okay. Now, it's possible we just left ourselves logged in from another place. You know, maybe we were working from home, maybe we're working from another computer somewhere, and it's possible somebody else is logged in as us. You know, these are all possibilities of how that might happen, but this is how we get that information about who is logged into this system and where they logged in from. We can look at the session login time, like right here, like when did they log in. So here, I logged in at 12:41 remotely, but I logged in. It's a little bit suspicious, right? But it could be not a problem. All right. Okay. All right. So these are some reasons here that it talks about why we might want to kick somebody off a system. Okay. What we can do is, again, if we cannot be contacted, or if we, ideally, what we would do is if a user needs to be logged out of a system, we would tell them, hey, we need you to log out of the system, and they would do it on their own. But sometimes they can't be contacted. It might be after hours. It might be that they left the office in a hurry to go take care of something regarding their family. You know, there's all kinds of reasons that they may not be able to do what we need to do and to log out on their own. So okay. Yeah. So anyway, so we talked about this already. I said something like this already, where reasons why we might need to get somebody logged out. Okay. So what we can do is we can see what's running, what's going on, right? And we can kill the user's processes, right? And then that would effectively, we can get them out of the system that way. Okay. So we can use that pkill command that we talked about in the last part, in the last little section, right? To be able to terminate, to kill, to get rid of all processes for that user. Okay. And the pgrep tells us, you know, what processes are going on. And obviously Bob is it's just an example. It's just an example user. No, hopefully no one would actually run multiple sleep commands, unless of course they were possibly, you know, trying to cause some resource overload on the system, right? But this is an example of a user where he's just waiting, right? He's got 3 shells that are just waiting, right? And so we need to get rid of those, right? So we need to kill those and be able to get rid of them. So here we say, okay, pkill, sigkill. Remember that's signal number 9. You guys remember It's not the term command, it's because terminate would allow it to clean up on its own. We want to kill it. We want to say, kill all signals that are related to Bob. Okay. And then if we go back and we look for any processes belonging to Bob, we get nothing. Right? Okay. So here, another possibility might be we could kill processes that are not the shell request. So again, if we go back, look at his list of processes. If we kill all of his processes, we kill his bash shell, we also kill all the sleep commands that he has going on as well. Okay, so this would kill anything related to Bob. Bob doesn't even get to keep his shell active at all either. Okay, so here, if we say, okay, let's terminate instead of the sig kill, right? Let's terminate. So remember the default. We're going to kill things related to this TTY3, which is this information here. It's where this stuff is running, where Bob is running this stuff. So when we kill that, what happens is when we go and look at what Bob still has active, all the sleep stuff is gone, but the bash is still there. So the bash, remember, that's the terminal. That's the login shell, right? So he still has that open. It's just all the sleep commands are gone. So this killed everything related to that, but left that shell open. So then if we say, okay, send the sig kill command for that terminal ID, then what's going to happen? It's going to kill the terminal ID as well. It's going to kill the bash as well. Okay. So if we wanted to see in a different format, so here this is like all the processes that Bob is running. If we wanted to see it in a tree format, to see, okay, how these processes how are they doing this? Well, this shell is producing these three. Okay. This PS tree command tells us not only what the processes are, but kind of in a tree format. So this shell, these three child processes belong to that shell. So then if I kill by process ID, right, this terminate, remember the signal I'm sending is that terminate signal. What's going to happen? It's going to politely ask those things to clean up. What it's going to do is it's going to not get rid of that. It's going to get rid of the three sub-processes that are inside of it. Okay, the child processes that have been, the children that have been created. So if we go back and look, what does Bob have? Well, he still has the bash. So you might think, wait a second, I thought I told it to kill this. This signal, the signal terminate, will work for any process that's a child process of a bash shell, the login shell. You have, in order to get rid of the login shell itself, you have to use the sig kill command. Okay. I hope that's clear. All right. Okay, wait a second. I'm sorry, I said that wrong. I was still explaining this stuff up here. This one here, because the dash P command is used, the dash P option is used, it's only going to kill child processes of this bash shell. Okay. So even with the sig kill command, it looks like you can't kill the bash itself. You would have to either kill the terminal based on the terminal ID, or you would have to up here kill based on the user ID in order to get rid of their bash shell as well. Yeah. Sorry, I said that wrong. The -p command is based on process ID, and so even that will not kill the bash itself. Okay. All right. So this would be a guided exercise we could take a look at, and we will after we get through these chapters. Okay. Let's see. Okay. Some other stuff that we might want to do, some information we might want to have to help us know whether or not we need to kill a process or let it run, would be for monitoring the activity of the processes. What is uptime and load averages? Like, what is the amount of resources that the process is taking? We can also monitor real-time processes, because this would be, for those of you who have any who've ever used the task manager in a Windows computer, this would be kind of in that same idea of being able to keep track of what CPU is going on, what memory usage is going on, what's the load average. All right, basically it's how much of system activity has it been using over the recent, less recent, and long term. Okay, and this can be very important for understanding, is the process, has it been running for a while, but more recently it's been using a lot more resources, and so that could mean something. So let's take a look at, let's see. Let me get to this whole the load calculation. I want to get to that information. Okay. All right, so here, all right. So we're going to be given 3 numbers when we go and look at the uptime, right? We look at the so for the load average values. Okay. So now this is basically how much has it been using resource allocation, resources, right? So a value below 1, so not these values below 1, right? But rather how much value per CPU below, is that 1, below 1, greater than 1, right? Is a value below 1 means that there hasn't been a lot of waiting. Okay, there hasn't been pretty good in terms of resource utilization. Means that processes have come in, they've a CPU, and then been processed and moved on. Okay. A value above 1 means that there's been some amount of service waiting times, meaning that the processes have come in, they want to get processed, they want to get, they want to execute, but they haven't been able to find a logical CPU. They haven't been able to find a processor to be able to service them, because the other processors are doing, all the processors on the system are doing things for other processes. So this process has to wait. Okay, and this is a load average across all processors and processes. And this isn't like a particular process right now is doing this. This is what is on average, how much waiting has had to go on, right? And this is the last 1 minute, the last 5 minutes, and the last 15 minutes. Okay, so what can we, what does this indicate, this example? Okay, I'm gonna, in case you haven't looked ahead there, all right, so here, this load average is, average processability across 4 CPUs, 4 logical CPUs. So if we divide by 4, so how much per CPU, right, then we find out this is like basically a 0.73, which is below 1 per CPU. So, basically resource utilization has been below 1 over the past minute. This means it's around 1.12 over the past 5 minutes and around 1.30 over the past 15 minutes. So what does this tell us? What do you think this tells us? What can we understand from this data? Like, what general trend are we seeing? Anyone? No? No one? Okay. All right, so I guess still a little too early for you guys to be awake. Are you guys just excited, not really here because of the last day of not having to be inside for multiple hours? All right, so what we can learn from this is that basically the system was running very smoothly over the past minute. All right, not a lot of wait times, maybe not waiting at all, really. Okay, the processors were, for the most part, well, for 27% of the time, were waiting on processes to come in. Like the processors were just being idle for 27% of the time over the past minute. Right. Then over the past 5 minutes, however, the system was overloaded by 12%, meaning that processes waited for processors to be available. Okay, we didn't have enough computer power, computer ability to be able to handle all the processes that were coming in. And over the past 15 minutes, it's been even worse. Okay, so it was overloaded by 30%. So what we can see from this trend is that approximately 15 minutes ago or so, the system was way overloaded, but over the past 15 minutes, it has handled those processes and gotten them completed, and to the point that over the past minute, it's actually been much slower now. So basically, what we can know from this is that the process requirements, the amount of processes that what we've been trying to do over the past 15 minutes has been slowing down. We have been slowing down our need of system to do stuff. Okay. Process sleeping for I/O due to busy disk or network resources are included in the count and increase the load average. So if we're waiting for things, right? If we have a process that's sitting on a CPU and it's waiting for the user to enter something before it will continue, that's counted. That increases the load average. Okay. Okay. Again, until resource saturation, a load average will remain below 1, right? Since tasks will very rarely be found waiting in a queue, right? Load average increases when processes wait, right? When processes wait in the queue for a processor to become available. Okay. All right. So as we get closer and closer to 100% of as we get closer and closer to 100%, right, we each additional request starts experiencing some wait time. Okay. So the tope command can tell us what the processes are that are running. Okay, we can monitor these processes. Again, these states, right, some of the states that we've talked about before, the zombie, the stopped, sleeping, running. Right, these are all some states that we need to be familiar with for when we see these things. Okay. These are some different extra commands, command arguments that we can give. All right. Sorry, no. When we're in the tope, it acts like the task manager. These are some keystrokes that tell us some things. Okay, we'll give some examples here. What we'll do is we will walk through. I think that's the end of this. Yep. Okay, so that's the end of chapter 7. What we will do is I will try to do this guided exercise, something like it, with you guys here, and during the third hour today, right? But I'm going to go ahead and take our break now. I'm getting a few messages from some other students. It looks like they were not able to find this meeting. So they are asking, why aren't we having class today? But we are. So I think I need to go help them figure out how to find this. All right. So what we'll do is, again, we'll end chapter 7 here. We'll continue with chapter 8 and get into chapter 9 in the second hour. And then we will do some guided exercise stuff in the third hour. All right. So let's take our break. I'll see you guys at 10:25, and we will continue on. Thanks.